Now, even though the title of this could be called Quotients of Monomials, what I like to think of the title of this lesson is something a little easier to understand, which would be simplifying expressions that involve fractions and exponents. So lots of fractions, lots of exponents. Let's go over here and talk about laws of exponents. So the very first law of exponents that we typically talk about is when you have a variable raised to a power, in this case let's just call it the second power, times a variable with the same exact base raised to a different power. So same base, different numbers. And we learned in the past that what we do here is we add these together. 2 plus 3 here, we add them, which is x to the 5th power. This should come as no surprise, and the reason this works is because this is x times x, and this is x times x times x, so they're all multiplied together, and there's 5 of them, and that's why we add them together. All right, so that's what happens when you have two terms multiplied together with the same base. Now we turn our attention, what happens when we divide terms? So for instance, if we have x to the 3rd divided by x squared, we add the exponents in this case. Well, in this case, what do? We take the top exponent and we subtract the bottom exponent from it. So 3 minus 2, which as you all know is x to the 1st power, which as you all know is just x. So it's very simple to see the symmetry here once you get it all in one place. When you have the same base, different exponents, you multiply, you just add the exponents. When you divide, you subtract the exponents. Now in general terms, over here I'll put another column here, general. And this is what you might see in a textbook. So for this first rule, what you might see in a textbook would look a little more formal. It might say x to the a times x to the power of b equals x to the a plus b. All this means is we add the exponents, just like I'm showing you with the numerical examples. And this one, again, showing a little more formality, would be x to the a divided by x to the b equals x to the a minus b. You're just subtracting the exponents top minus bottom. Now, just to take a little bit of a side, the reason this actually works, the reason I'm going to go into it is because we'll use it during our problems here, is the following. The numerator here is really written as x times x times x. There's 3 of them, right? And the denominator is x times x. There's 2 of them. So since you have a lot of multiplication going on in the top and the bottom with the same variable, you can cancel terms. We have an x common to this x, so they divide away. You know, we say things cancel in algebra when they're on top and bottom, but really what's happening is you divide them away. X divided by x is 1, just like 2 divided by 2 is 1, or 17 divided by 17 is 1. So this x divided by this x is 1, so they disappear. Or they don't disappear, they go to 1. This one cancels with this one also, so all you have left is that x. So notice that what's really happening, no matter how you represent it, if you think of it as multiplication with canceling, you get an answer. If you think of it as taking the top minus the bottom, which is really what you're doing, you're taking the top minus the bottom to give you what's left over, either way works. And we will use both ways of thinking about these as we do our problems. But essentially, you subtract the exponents. That's the kind of the simplest way to think about it. Now, what if we have a product of 2 different variables, x times y, and we raise that to an exponent? So what happens is this exponent gets applied to each term almost like it's distributed in as follows: x to the 3rd, y to the 3rd. You take the exponent, you multiply it, or I shouldn't say you multiply it, you apply that exponent to every term in there. And then if you had to generalize this over here, the way you would see it on a textbook would be x times y to the a power would be x to the a power times y to the b power, taking that exponent and applying it to everything inside, to every term inside. All right. Now this is what happens when you're applying it, when you're applying this to 2 different things on the inside. What if you have an actual exponent like x squared, but then you raise that to another outside power? So what ends up happening is you take these exponents and you multiply them together. So what you're going to get is x to the 2 times 3, which is x to the 6th power. So exponent raised to an exponent, you get x to the 6th power. And then if you were going to go over here and write that a little more formally, it would be x to the a raised to the b power is x to the a b. Now all of these things I'm writing down on the board kind of quickly, and that's because I've had an entire lesson in exponent laws where we blew all of this stuff out, and I can show you by writing down how the exponents work and how it cancels that it comes out to always be multiplying these 2 exponents here. So if this all seems foreign, go back and watch the other lesson. I'm just trying to get them on the board so that we can kind of reference them during this lesson here. The last one I'm going to have is if we have a fraction, x over y, and we raise it to a power. In this case, let's say to the 2nd power. What happens is we take this exponent, just like we did here, and we apply it to everything inside, but we have to apply it to the top separately from the bottom. So the square gets applied to the top, the square gets applied to the bottom, just like this. So if you wanted to write that down a little more, mathematically, then you would say x over y raised to the power of a is x to the a over y to the a. So again, just really quickly, you have two things multiplied. Let's go to the general column. Since we explained it with numbers, we'll go to the general column. You have two bases that are the same with different exponents. You just add the exponents if they're multiplied together. If those things are divided, then you just have the same base and you subtract top minus bottom to get the new exponent. If you have two things multiplied together with an exponent on the outside, you kind of distribute this, and actually I have a typo here. This is going to be x to the a, y to the a as well. Sorry about that. You take this a and apply it to the x, you take the a and you apply it to the y, you get x to the a, y to the a. So that would be the general term, just the way we have it here. So exactly the 3 going in there. Sorry about the typo. And then for this one, when we have a power raised to a power, we just multiply the two things, just like we did the 2 times 3, giving us the 6. And then when we have an exponent applied to a fraction, we have to apply it to the top and to the bottom of the fraction. All right, now that we have all of these on the board, we want to jump right into the concept of simplifying these quotients of monomials. So let's say you had a problem that looked like this. 18 x to the third power divided by 6x. All right, so what you have here, what I'm going to do is I could start scratching through and all this stuff and marking it up, but what I want to do is write it over again so I don't kind of mess up the original thing that I wrote down. 18x to the third over 6x. So the first thing you do is you look at the numbers and you realize that 6 times 3 is 18 and 6 times 1 is 6. So another way of thinking about it is anytime you have numbers on the top and the bottom of a fraction, you always want to simplify that fraction. Just think about simplifying fractions. Anytime you have a fraction, you always think about what can I divide the top and the bottom by? What is the largest thing I can divide the top and the bottom by to simplify that fraction into lowest terms? So here I know I can divide the top by 6 and the bottom by 6 because they're both divisible by 6. That's the biggest thing. So 18 divided by 6 is 3, so you strike it out and put a 3, and 6 divided by 6 is 1. So what's going to happen is, when I rewrite the problem again, I'm just going to have a 3 and a 1 here instead of the 18 and the 6. And then I look over here at the exponents, and there's a couple of ways you can think about it. Let me go ahead and write the next part of the answer down, I guess. So what I'm going to have is I'm going to have a 3 here, and then I'm going to have to figure out what to deal with here. Now, what you need to look at is commonality in the top and the bottom. I have 3 x's on the top, x times x times x, and I have 1 on the bottom. So only have 1 on the bottom, so this 1x can cancel with one of them up here, but that'll leave 2 behind. So I strike through only the 3, rewriting it as a 2, letting me know that this single x canceled with only one of these, leaving me 2 behind. So then when I rewrite the problem, I come over here, and I say, well, all I have is a 3, I still have an x here, and I have it to the second power. On the bottom, I have a 1 here, but I struck through this x, so there's really nothing else on the bottom, it's just a 1, and so I don't have to write a 1 here. So the answer I get is 3x squared. Now again, I told you there's always more than one way to solve problems in algebra, so you need to start thinking about different ways to think about it. So the first way, the way we did it here, was the idea that when you have exponent on the top and exponent on the bottom, what you're doing is you're slicing through all of the commonality because they're dividing away. So in this case, we had 3 x's on the top and we had 1 on the bottom. So we can only strike through the 1 on the bottom and we only could strike through 1 on the top, leaving 2 behind. That's why we got our answer. But notice another way you can think about it is, remember the exponent law for division is we just subtract the exponent. So we have exactly the same concept over here. 3 minus 2 is 1 in this example. 3 minus 1 means the exponent will be 2. So there's really multiple ways to do it. I can strike through like this, which is what I typically do in my problems, or I can just look at it and say, well, the new exponent has to be subtracted. 3 minus 1 is 2. And then the 18 divided by the 6 gives you 3. All right? So that's just the first problem. We're going to get to a lot more complicated things, but these are important concepts because soon we're going to have lots of variables and lots of exponents to deal with. So what if we had, for the next problem, negative 12 p to the third power times q, all divided by 4 p to the second power q squared. And as I said, I don't want to mark up my original problem, so I'm going to do a lot of rewriting in this lesson. You may or may not do that on your paper, but I always write it down again, because here's the problem. If you start scratching up the thing you write down, then it's going to look like this. It's going to be marked up and you'll never be able to see what you started with. Besides, I'm using colored markers, but when you're using a pencil, you can't really, there's no color there, so it's hard to see what you wrote down initially. So write it down again before you start messing around with it. So we talk about the numbers first. I know you all know that 12 divided by 4 is 3, but I want you to think about dividing the top and the bottom by some common number. So we'll divide the 12 divided by 4 is going to give me 3, and the 4 divided by 4 is going to give me 1. The negative doesn't divide away with anything. It's still there. So we still have a negative, but this 12 becomes a 3 and the 4 becomes a 1. And then we look at the p's. So we say, what's going to happen here? We have 2 p's here and we have 3 p's on top. So we can use both of those p's to cancel with 2 of them up here, but it's still going to leave a 1 behind. So I put a little 1 there to let me know this p still has a first power, right? And then the q's here, I have 1 q on the top and 2 q's on the bottom. So 1 q from the top can cancel with 1 from the bottom, leaving 1 behind. So you see, you get lots of markups here, which can be hard to read, but you know, that's the way it goes. So you still have a negative, you have a 3 here, and then what you have is on the top you have a p to the first power, so I don't need to write the first power, right? This is gone, so on the bottom I have a 1, I don't need to write that. The p squared is completely marked out, and the q is to the first power. So that's all I have left, negative 3 p over q, and that's the final answer. Now again, there's lots of ways to think about it. You can think about it like this. Instead of doing the simplification here, you can think of 12 divided by 4 gives me 3, and of course the negative is still there. And then for the p's, you could just subtract the exponents. 3 minus 2 is p to the first power. So again, there's lots of different ways to think about it. We can do it the way we've done it here, or you can take a step back and say 12 divided by, or negative 12 divided by 4 is negative 3. That's where that comes from. And then you can also think, I want you to think about just the p's for a second. What we had, the p's here, was p cubed over p squared, which is, as according to the rule over there, top exponent minus the bottom exponent, which is p to the first power. So that's why this is p to the first power. And then we can also look at the q's, right? We had a q on the top and a q squared on the bottom. So this is a q on the top, which is q to the first power. So if you're going to do it by subtraction, you'd say 1 minus the bottom here, 1 minus 2. But notice what you get here is, what is 1 minus 2? Negative 1. Now we have not covered negative exponents in this class yet. We're going to cover negative exponents a few lessons from now. But it's kind of a preview to let you know that there is such a thing as a negative exponent. And you need to get comfortable, some sort of way, with seeing negative exponents. For now, we're not going to go into it too much because I want to do a complete lesson on that. But if you do this thing by subtraction and you happen to see a negative exponent, all it means is that the q to the first power doesn't live upstairs. The negative exponent means that the q to the first power lives downstairs. So anytime you see a negative exponent in algebra, it means that you can write it as a negative exponent. Sure, you can leave it there. Or you can move it downstairs underneath the fraction and make it a positive exponent. That is what a negative exponent means. Positive exponents live on top of the numerator. Negative exponents get moved downstairs. Notice he's a q to the first power. The negative implies or means that that exponent actually lives in the bottom of the denominator. So we're going to get into a whole lesson like that. So because of the fact that you sometimes get these negative exponents, and because of the fact that we haven't really talked too much about negative exponents yet, typically the way I like to solve these problems is just by canceling things. And that's how I'm going to solve the rest of these problems. The only other thing I'll say before we continue solving these problems is notice that we had p cubed, let me gesture here, we had p cubed and we had p squared. So we have 2 p's and 3 p's. So when I said we can sacrifice or cancel both of the p's on the bottom, notice that I drew the strike through the 2 and also through the p. That tells me when I go to my next step that I've killed all of it down here. If I only strike through the exponent, just through the 2, and write a number next to it, that means the variable is still there with a new exponent. Here I struck through the 3 and I wrote down a 1. That means it's p to the 1. Here I struck through the variable. That means it's gone. Here I struck through the p squared. That means it's gone. And so you need to kind of get you practice it. It all takes practice, but it's just a methodology that we use to help us remember what we're doing in the next step. All right, so let's go and solve a few more of these. We have a few more problems. They're going to get more complicated, but they're all going to follow exactly the same pattern as what we have done here. What if we have negative 15 u to the 5th power, v to the 3rd power, and on the bottom we will have negative 25 u to the 4th power, v to the 2nd power. Now again, same sort of thing. I'm going to mark it up over here. So 15 u to the 5th power, v to the 3rd power over negative 25 u to the 4th power, v squared. So we have to decide what to do. First, we go and tackle the numbers. We have 25 and 15. So immediately you should think you can divide both of those by 5. But we also have negative divided by negative. So you can kind of strike through both of those, making them positive, because you all know that negative, anything divided by negative always gives you a positive. And then for the 15, we'll divide by 5, giving us 3. The 25 divided by 5 will give us a 5. So we have new numbers in there, because we simplified that fraction. And then we look at the u's. There's 4 on the bottom and 5 on the top. Everything's multiplied, so I cancel all 4 of these u's, meaning I strike through the whole thing, including the u and the exponent. On the top, I only have 1 left, so I only strike through the 5, and I write the number 1 next to it, letting me know that I still have a u to the 1st power. Now on this one, I have 2 v's and 3 v's on the top, so I can cancel both of the v's. I strike through the complete thing, including the base and the exponent. Here I strike through only the 3, leaving me a 1 left, because, you know, if I have 2 on the bottom, I cancel 2 up here, I have 1 left. So you see what you're doing is you're subtracting exponents when you're writing the new numbers down up here. All right? So then what we're going to have for our final answer is going to be positive 3u to the 1st power, v to the 1st power. On the bottom, we will have 5, but notice we struck through all of this. It's totally gone, so there's nothing else left except for the 5 on the bottom. So we have that as our final answer. So again, that's doing it in the method of canceling things, but I want to show you how to think about different things. So let's talk about, forget about the numbers, let's talk about the u to the 5th, v to the 3rd, over u to the 4th, v squared. Let's talk about that. So what you're going to have, you have u and u, so you have these guys on the top and the bottom, different exponents, same base. So what you can have is u subtract the exponents, 5 minus 4, and then you'll have that multiplied by the v terms. So you have v, and you subtract these exponents, 3 minus 2. You see, all we're doing is using this rule here. When you multiply exponents or terms with the same base, different exponents, you add. But when you're dividing terms, you subtract the exponents. So all we're doing is we're saying we've got a division here and a division here. So we subtract the exponent, and of course what you get is u to the 1st times v to the 1st, which is exactly what we got for our final answer. Different ways to think about it. It's okay to think about either way to do it. You can totally use this, or you can do the cancellation method. I typically do the cancellation method. It becomes a little easier when the problems get harder, I think, in order to do that. Also, later on I am going to introduce negative exponents, which it just depends on the problem. There's no right answer, but typically I use this cancellation technique more than anything else. All right, now let's move on to something a little different. What if we have 3 times r over s squared, and that's a fraction, all raised to the 3rd power. All right, now you look inside of here first and you try to simplify this, but you can't, because 3 and 1 you can't do anything with, r and s squared you can't do anything with. So you go back to your exponent laws, right? When you have a fraction of any kind with an exponent on the outside, you apply the exponent to the top and then the exponent to the bottom. So the way we're going to write that and make it clean is we're going to apply this to the numerator. But the numerator is a complex thing with 3r. We're going to raise that to the 3rd power, and then we're going to apply that to what we have here. S squared is the denominator, which has to be raised to the 3rd power. So you see, you're taking and applying it to the numerator, which is a complex thing, and then you apply it to the denominator, which is kind of a complex thing too. But notice the numerator is 2 things multiplied together, and we have a rule for that. When we have 2 things multiplied together to an exponent, you apply the exponent to each one. And also, an exponent raised to an exponent means you multiply the exponents. So now we have to apply both of those rules here. So right now the 3 would get applied to the 3, making it 3 cubed. The r would get that exponent applied as well. But on the bottom, it's an exponent raised to an exponent, so it's 2 times 3 is 6. All right, and then finally, what is 3 to the third power? 3 times 3 times 3. So 3 times 3 is 9, 9 times 3 is 27, r cubed over s to the 6. And I know you might want to do more with this because you don't like all those exponents, but you can't, because this is a different base than this one. You see, all of these exponent laws, they only apply if the base is the same. It's like peanut butter and jelly. You know, I know peanut butter and jelly, they go in a sandwich together, and we love to eat peanut butter and jelly, or ham and cheese or something, right? They go together. But in algebra, things can really only be worked on together or combined if they really are identical in some sense. So the bases have to be the same in order to add these exponents or subtract the exponents, or even when we do other things like adding like terms, everything has to be the same, right? So here we have an r cubed and an s to the 6. Sorry, we just can't do anything with it because these are completely different items. You can't just combine them together. So we leave it like this. All right. The next one we'll do is similar to this one. It's actually a little bit easier, but let's say we have 3s over t squared. That's a fraction, and we're going to multiply it by another fraction, which is going to be s squared over t. So when you look at this, when you first look at this, it can look a little intimidating, right? Because none of us, when we first learn fractions, really love fractions, right? But you kind of get used to it and you can handle it. And then you start dealing with fractions that have terms on top, exponents on bottom, exponents on top. It looks very difficult. My advice to you is forget about the fact that it's a fraction in algebra. Forget about the fact that it looks complicated. The exact same rules of fractions apply to algebraic fractions as apply to any other fraction. In other words, to add any two fractions, you have to have a common denominator. Same thing is true if it's an algebra fraction. You have to have the same thing on the bottom. When you multiply fractions, no matter if it's a number fraction or an algebra fraction, remember what happens if we have something like 1/2 times 3/4. How do we do it? We don't get a common denominator for this. We just multiply the tops, giving us 3, and we multiply the bottoms, giving us 8. Multiply the tops, multiply the bottoms. So the exact same thing happens here. We multiply the tops and we multiply the bottoms. So when we multiply this together, we get 3s, but we have to add these exponents because it'll be 3s times s. So we can add those exponents because we're multiplying the s terms together. So it'll be 3s cubed, and then t squared times t is going to be adding those exponents. 2 plus 1 is 3, so we get t cubed right here. So we get 3s cubed over t cubed. So again, the final answer is 3s cubed over t cubed. And as much as you want to combine these, you can't subtract exponents or anything because these have different bases. So you can't combine them. They're different. All right, we have two more. They're not difficult, but we want to get through these. What about 3x squared divided by y squared times 3y over 6x? All right, so it's the same kind of thing. We have to treat them as fractions. This is a fraction. Yes, it's ugly. I understand that. This is a fraction. Yes, I understand that it's ugly. But it's a fraction nonetheless. So when we multiply them, we treat them the same way as everything else. So what we have is multiplying the tops together, 3x squared times 3y, right? And on the bottom, we have this y squared times 6x. So we just handle the multiplication. Now we can always multiply the numbers together. That gives us 9. We'll have x squared y. And on the bottom, we'll have a y squared with a 6 in the front. So we'll have a 6. Let's write it as x first and then y squared. Now you see this kind of problem looks exactly like some of the earlier problems we have. So we need to simplify that. Let me go ahead and write it again. 9x squared y, and then we'll have 6xy squared. So again, we try to simplify. We'll divide top and bottom by 3. So 6 divided by 3 is 3. 9 divided by 3 is, 6 divided by 3 is 2. And 9 divided by 3 is 3. And then for the exponents, we have 1x and 2x, so this entire x cancels with one of these, leaving one left. 1y on the top cancels, so we scratch that out, and we have only one left because we had 2 and now we have only 1. So then we can write the final answer as, on the top we have a 3x, and on the bottom we have a 2 times y. Everything else is gone. The y is gone, and so on. So we have 3x over 2y. That's the final answer. Now, always in algebra, there's always multiple ways to do things. You're looking at this probably thinking of a slightly different way to do this. If you see a different way to do it, great. That's totally fine. There is probably 3 different ways I could do this problem. And none of them are right or more correct. It's just different ways of doing it. Let me give you a couple. I'm not going to solve it again, but let me do another example of how it could be different or how you could think of it differently. Right away, you see this is 3 divided by 6. So immediately before doing anything else, I could just simplify this fraction and make this 1/2. So it would be y over 2x, right? So if I simplified this, the 3 would go away, the 2 would be on the bottom. Notice we have a 3 and a 2. So the numbers would ripple through exactly as we got to this final answer. Here in this step, we multiplied the tops, multiplied the bottoms, then simplified, but we could simplify the numbers first and we'll get exactly the same answer. Also, many of you know, because we've done in previous problems, that we can simplify all of this if we want to, even before doing the multiplication. For instance, you know it's multiplied, so when you have a fraction times a fraction, if you have something in the top here, you can cancel with the bottom, and you have something here, you can cancel with the bottom here. Because in the end, you're going to multiply them all through anyway on the tops and on the bottom, so you can simplify before you multiply the fractions, or you can multiply first like we've done here and then simplify at the end. So in other words, I could look at the x squared and the x and I could cancel the x here and cancel one of these x's straight away. I could cancel one of the y's straight away. I could simplify the numbers before I do any fraction multiplication and then multiply the fractions and I would get exactly what I've done here, which is doing all the multiplication first and then simplifying. Is there a right way? No, there's no right way, but there's different ways and that's okay. As long as you know what the different ways are and what's legal, I'm happy. Final problem, r times s squared times t cubed over r cubed s squared t. So now we have 3 variables instead of just 2. I'm going to rewrite everything so I don't mess anything up. rst cubed over r cubed s squared t. All right, so we look at the r's. We have 1 r and 3 r's. So this single r can strike out with this, giving me 2 r's left over. I have an s squared and an s squared, so the entire s squared can cancel with the entire s squared. Notice I struck through the whole thing, so it's gone. One of these t's can cancel with one of these t's, leaving me 2 left over in the final answer. So the final answer that I'm going to get, I have no r's left, no s's left, but I do have a t squared on the top. And on the bottom, I have an r squared, but I don't have any s's or t's, so it's going to be r squared. Let me double check. T squared over r squared, that's the final answer. Now, let's look at it by subtraction. What we have here for r's, let's just do it down here, r over r cubed. If this was the problem, I told you you can subtract exponents. So you have r 1 minus 3, 1 on the top, minus 3 on the bottom. R to the negative 2. I told you we haven't done negative exponents, but when you see a negative exponent, it just means that it really lives downstairs as a positive version. So negative exponents are a way of writing fractions without really putting a fraction bar, right? You can write it as a negative exponent, or you can just move it downstairs and make it positive. That's why it lives down here. So when you see this, it means it really lives downstairs. For the s terms, it would be s squared over s squared. That's just the s terms, right? Which is s2 minus 2, which is s to the 0. And we're going to do a lesson on this later on, but I'll give you a preview. Anything raised to the 0 power is 1. So that's why there's no s's in our final answer, because it all went away to 1. And then finally, we have t. So we have t cubed over t, which is t to the 3 minus 1, which is t squared, and we have t squared in our final answer. So if we did not do this canceling, what we would get, for the t terms, we would get t squared, which means he lives in the numerator. We would get 1 for the s terms, which means he disappears completely. And for the r terms, we would have an r to the negative 2, which means he lives in the bottom as r squared, which is exactly what we've gotten here by using the cancellation method. I prefer for you to do things like this by canceling initially, and then as we get a little more practice down the road with negative exponents, then you can do it any way you want. So make sure you understand this. It's very important for you to get paper out and not just watch me do these problems. Get your own paper, go back through these problems, write them down yourself, and do them yourself. When you have confidence in what's going on, then follow me on to the next lesson. We're going to do more problems with quotients of monomials in algebra. Learn anything at mathandscience.com.